everyone, this is Suvarchala, working as an associate professor at Institute of Aeronautical Engineering. So as a part of design and analysis of algorithm lecture series, in this video, I'd like to discuss about one of the strategies of designing an algorithm and also one application of the respective strategy, that is divide and conquer strategy. So while designing an algorithm, we discussed already how an algorithm is going to be written and on which parameters we need to consider, which algorithm is better one based upon, and how these respective parameters are going to be, that is time complexity or space complexity, etc. are represented. Standard notations by using our asymptotic notations. These are all discussed in previous videos actually. So while discussing about the algorithms, there are two phases we need to consider. The first phase is going to be designing an algorithm, second phase is analyzing algorithm. These two are two areas of algorithm related concepts actually. That means first we supposed to learn what are the standard designing techniques are there, or designing strategies are there. And by using strategies, these strategies, if you are going to write algorithms, so how the algorithm can be improvised, quality of algorithm can be written for any given application or given problem, to find solution of a given problem actually. So in these two phases, we discussed a little bit about the analysis in the previous video. In current video, I'll discuss about one of the strategies of the designing an algorithm. For designing an algorithm, various strategies are there, standard strategies are there, and by using these strategies or combination of these strategies, or based upon this, a new strategy can be devised by ourselves while writing an algorithm for solving an application or for solving a problem. So that's why first we supposed to understand what are the various strategies or standard techniques are available to design algorithm, and what are the advantages and disadvantages of all these standard techniques. Some of the techniques are divide and conquer strategy, greedy technique, branch and bound, dynamic programming, and so on and so forth. As a basic strategy, we will discuss in this video about the divide and conquer technique. The term itself indicates what is divide and conquer. That means the problem has to be divided into sub-problems, and after solving each sub-problem, the results have to be combined again. So this divide and conquer can be considered as divide your problem into sub-problems, solve the sub-problems, and conquer the solutions. That means how much time or how many number of times this type of processing has to be considered. Once, twice, thrice, or how many number of times. This process is continued as long as we can solve a problem independently with smaller data actually. That is, this divide concept is going to be continued. This process, these three steps are going to be recursively done. Recursively means recursion. By using recursion, we will do generally this type of implementation of divide and conquer. And recursively, this is going to be done by us such a way that if a problem is going to be independently solvable, because division is not required. Generally, when such type of division is required, if the problem is complex or our input size of data is very large, with which solving a problem may take more time also. So that's why we will use this concept as long as the problem is going to be, sub-problems are going to be divided further, again solved, and sub-problems are divided further, and so on and so forth, till we will get a problem of size k such that that problem can be solved independently, easily. So that's why whenever we are going to have multiple things. For example, here we are using multiple projects are there. The projects are going to be divided among various people, and division is going to be done in such a way that the project can be done by the person independently. So this is going to be done by recursion. So recursion means, what is recursion? Recursion means it has to be applied for iteration is different, recursion is different. Recursion is going to be continued till the last recursive iteration. Then if it gets solved, then reversely the process is going to be get done. So in this recursive examples, first you observe here. So this is going to be recursion. Then the smaller one is going to be got result. Then the larger ones are going to be considered by us. That means each phase of result is going to be based upon its next phase results. So the base results have to be get solved so that the next levels of results are going to be easily get solved. You please see on these diagrams are showing some recursive examples. So you on your inner ways, layers are there, layer by layer by layer by layer. So inner layer has to be get first, then it depends upon the outer layer, and so on and so forth. Similarly, dolls or picture you observe here. So what is a recursion actually? Recursion definition is recursion means define an entity in terms of itself. So recursive definition is defining an entity in terms of itself. Generally in computer science we will use recursive functions. So we will define a recursive function. So what is a recursive function? A function which calls itself is a recursive function, or a function calls other function in turn calls the first function, then it is going to be called considered as a recursion. That means recursion is a cyclic process here. But when it is going to be come out of this type of cyclic process, if it is called itself means every time it calls itself, when it's supposed to stop, so some constraint must be there. The constraint is based upon, we will call it as generally the base constraint, we will call it as. That is, we will call it as a basic case or base constraint. This is a primitive constraint for which the solution is given. And the remaining recursion levels are going to be based upon this primitive constraint. So this recursive process is continued till this primitive constraint satisfies. At the level of primitive constraint, the solution is given so that the next higher levels of the solutions are going to be easily computable by us. So recursive is going to be basis, the most primitive case of entity are defined without referring any entity, and inductive cases will be there. Inductive case means new case of entity that are defined in terms of the simpler cases of entity. So various kinds of recursive sequences are also there in our notations actually. A sequence is an ordered list of objects which is potentially infinite. And we denote kth object in terms of in a sequence so that if you are able to understand what is kth object, finding the sequence sum or product whatever it will be depending upon the sequence is not a big deal for us. That means we have to define properly the kth object of the sequence. So a sequence is, for example, a recursive sequence is defined in terms of naming that particular sequence itself. First few values are going to be specified in terms of the sequence, and it will give a value for a smaller values actually. The latter values in the sequence will be defined in terms of the earlier values, then we will call it as a recursive sequence. For example, you just observe S1 of 2, S of 1 is equal to 2. That means if the value of n is equal to 1, it is defined as 2. And Sn is equal to, for all other n's, recursive case, this is base case. If n value is 1, the function returns value 2. If that sequence returns the value 2. and if S of n, nth term is going to be defined as 2 multiplied by S of n minus 1. What is n minus 1 again? Previous term. Again in the previous term, again it will be defined as S of n minus 2, S of n minus 3. So this is going to be continued till we reach this n minus some kth value as a 1 actually. Once it is solved and the result is used for further steps and previous steps, and it can be get solved. So for example, if this you are considering this equation, let us assume that I'll take n value as 5. So what is my S of 5? S of 5 is equal to 2 into S of 4. N minus 1 no? So that's why. So what is this S of 4 again? 2 into S of 3. N is my 4 now currently. So that's why 2 into S of 3. Then what is our S of 3? S of 3 is going to be considered as a 3 into S of 2. N minus 1 no? Now current N is 3. Now S of 2 is defined as and 2 into S of 1. But S of 1 is, what is S of 1 value? 2. So this is going to be considered. Then how to calculate? 2 into 2 is 4. This is S of 2 value. 4 into again 2. 4 2s are 8. This is S of 3 value. 8 2s are 16. This is S of 4 value. 16 2s are 32. That will be the S of 5 value. Recursion. So it satisfies base condition. Till base condition satisfies, these terms are continuously generated, and once the base condition satisfied, the value was introduced. So that what happens? The respective value is used for finding the solutions of the previous levels actually. Similarly, one more example, this can be represented like this. T of 1 is equal to 1. You observe it, this sequence can be represented by using an equation. T of 1 is equal to 1 and T of n is equal to T of n minus 1 plus 3. This is another one kind of. For n greater than or equal to 2. For n is equal to 1 defined, if it is greater than or equal to this. This is also a recursive case. The first one is base case and the second one is recursive case. Right? Such type of expressions or equations are known as generally recurrence relations. Recurrence relation. So what is recurrence relation? A recurrence relation is an equation, a relation in which the equation calls itself. Then we will call it as a recurrence relation. For example, when we would like to try to solve certain problems, for example, factorial, Fibonacci sequence, because the same process has to be generated, no, we can use this type of recursive functions. This is Fibonacci sequence, f of 1 is equal to 1, f of 2 is equal to 1, and first two numbers are generated, given as input. From f of 3 onwards, we will use this recursive case. That is f of n is equal to f of n minus 2 plus f of n minus 1. Sum of the previous two terms, this is recursive. Then what is the sequence? First one, 1, 1, 1 plus 1, 2, and 2 plus 1, previous 2. So 3, next 2 plus 3, 5, and so on and so forth. So that means here, this recursive case is solvable for the base condition. What is the base condition? F of 1 value, f of, for example, I would like to generate f of 10. I suppose to note f of 9 and f of 8. F of 9, f of 8 and f of 7. Again f of 8, f of 7 and f of 6. And so on and so forth. When I am coming to f of 3, f of 1 and f of 2, which are available to me, I'll reversely calculate the values actually. That means the recursively defined functions, equations or sequences are solved based upon the base condition actually. So the recursively defined entities are typically proved by using our induction method, and also we can prove by using some direct definitions also. So for example, Fibonacci sequence f of n plus 4 is equal to f of n plus 2 minus f of n. This is one expression, and f of n plus 1 plus f of n minus 1, 2, etc. Recursively defined operations will be there. By using these operations, we can define some functions also. For example, multiplication. I want to multiply m star n. How to multiply m star n? M star n is equal to m star n minus 1 plus m. A sequence of additions actually. What is again m star n minus 1? M star n minus 2 plus. Again we are adding m plus m. And so on and so forth. It is a recursive. This process is continued till we have a value of m star is equal to n minus 1 value, some n minus some 2, 3, 4, etc. I'll get the result of this as a 1. Generally, m star 1 is equal to 1. We will use this and we will reversely calculate as explained earlier slide actually. One more example there. Recursive definition of exponentiation. We know, all of us know that a power 0 is equal to 1. Based upon that, I can calculate a power n. What is a power n? A power n is nothing but a power n minus 1 star a. Recursive definition. Factorial operation also same. F of 0 is equal to 1. But f of n is equal to n star factorial of n minus 1 for n greater than or equal to. That means all these operations, factorial, multiplication, exponentiation, all these can be defined by using some recursive expression or recursive equation. Then we will call it as the recursive operations. For example, we can define for all these things also. Recursive definitions can be considered for all these sequence of 1, 3, 9, 7. Every term how it is generating? It is generating 3 power some n value. So 3 power n is equal to nth term we are going to generate. We are going to consider 3 power n minus 1 multiplied by 3. Same example, second example. Every time it is half. So the term nth term is equal to t of n is equal to t of n minus 1 by 2. Right? We are going to consider by defining all these things. So by using this, if you want to solve such type of recursive expressions or recursive equations or sequences, we will use some algorithms can be written by us. We will call them as a recursive algorithm. So a recurrence relation exists for an operation, then the algorithm for such recurrence relation can be written by using two techniques, iterative technique and recursive technique. Either of them are going to be valid results. Of course, both of them are having its own advantages and disadvantages. So all of us are aware of that factorial of n. So a factorial of n can be considered by using a small iterative technique or as well as a normal recursive procedure also. If it is iterative technique, I will consider my factorial is equal to 1 and I will write my for loop for I is equal to 1 to n factorial f is equal to f star I. That means every time we are multiplying the existing value. This is a repetition or iteration, you can say. So same thing I can write recursive. For example, I am writing a function fact of I. Let us assume that or fact of n I am using. So I'll write a base condition first. If n is equal to 1, return 1. N is equal to 1 or you can take n is equal to 0 also. Return 1. Else call itself factorial of n minus 1 star n. That means this is iterative procedure. This is a recursive procedure. Both can be used by us. Both are having advantages and disadvantages. Recursion seems to be very simple actually. Because complex problems, when we are writing complex problems and when we are using recursive procedures, we can write by using a less number of statements. You can name, for example, tree traversal techniques. If it is non-recursive procedure, each algorithm consists of almost 15 to 20 lines. But is recursive only a single line. It doesn't mean that recursive is efficient. Why? Because in case of recursion, all these previous values must be stored, no? Those are going to be stored in a stack, internal stack is going to be used. Because of that, internally it is complex process. That is, it uses stack and stack applications, stack operations. That means it needs extra memory as well as the stack operations means it will take more time also. So that's why we have to choose a proper technique. Just now we compare these two, no, similar to that. Proper technique while solving a problem so that our algorithm is going to be more efficient. So this example is given, s of 1 is equal to 2 and s of n is equal to 2 into s of n minus 1 we considered to calculate the 2 power process. Right? So we started our technique. One of the strategies is divide and conquer. Why we moved to the recursion? Because while solving any of these such type of algorithms following these strategies, we need recursive process actually. So that's why we discussed now recursion. So that's why whatever the algorithm or whichever the algorithm we are going to write for an application, that particular algorithm is going to be written as a recursive algorithm also. If it is a recursive algorithm, we can represent it by using a relation known as recurrence relation. By solving this recurrence relation, we can analyze the time taken or a space considered by the respective algorithm actually. So this is the link between among these strategies, recursion and analysis. So that's why in this video I introduced the recursive process and we'll discuss general method of divide and conquer and with a small application. And in the next application of divide and conquer, before that we'll discuss about the recurrence relations also. How to solve the recurrence relation. So what is divide and conquer? We already explained. So given a function to compute on n inputs, the divide and conquer strategy suggests splitting the inputs into k distinct subsets. K may be any value between 1 and n, yielding k subproblems. So these subproblems are going to be solved. If those are not able to solve, again it is going to be further divided subproblems and each subproblem is going to be solved. So this process is going to be continued so that the subproblems can be solved independently and all these solutions are going to be combined all these solutions and so that we will get the solution of the whole problem. So subproblem division is continued as long as the subproblem is relatively large. If the subproblem can be solvable, then it is going to be solved so that further previous levels can be solved by using the current level of the combination of the solutions of the subproblems actually. So that's why we will call it as a divide and conquer, because remember that each subproblem must be of the same type, original problem type. Each subproblem is in different types of subproblems, it's not possible. Application of this divide and conquer. So when we are dividing our problem into subproblem, each subproblem is of the same type of the original one. Then only the same logic can be applicable, no? So that's why it can be solved by using our divide and conquer strategy. Of course, other than that, various techniques, other techniques will be there that can be used by us. So for this D and C, that is divide and conquer, D and C we will call it as initially, it will invoke itself while after dividing into subproblems. This process is continued as long as your subproblem is a small p which can be solved independently. That is, the input size is small enough that the answer can be computed without splitting, that otherwise the S is going to be invoked for the current input size also. So this divide and conquer is going to be combine a function that determines the solution to a problem P using the solutions of K subproblems actually. Let us assume that the size of the problem P is n, then the size of the subproblems are going to be k, then n1, n2, etc. nk, k subproblems we considered here, and compute each subproblem by using the same technique, DNC technique, in a recurrence relation. So that's why we will represent this, any of divide and conquer can be represented if the algorithm was written by using a recursive procedure. As I explained earlier, an algorithm can be written either by using recursive procedure or iterative procedure. But most of the time we will use in this design algorithms, recursive procedures are going to be used by us. If it is used recursive procedure in algorithm, then that particular algorithm can be represented or described by using a recurrence relation. So for example, in divide and conquer, it is going to be like this. T of n is equal to g of n for small values of n. That means final solution was found. Otherwise, t of n1 plus n2 plus etc. up to t of nk plus f of n. Where t of n is the total problem of size larger size, that is of size n. G of n is the time compute the answer directly for small n. And f of n is the time for dividing, because the problem we are dividing, no? Again we are combining results. Again division of the problem as well combining the results of the problem. Subproblems is also takes some time. So that's why we are using this f of n. F of n is the amount of time taken to divide our problem into subproblems. Again combining the subproblem solutions into original problem, we are using this one. And t of n1 is time taken for n1 size, time taken for n2 size, etc. Again, these are repeatedly, recursively called this one only. Again, if it is small enough, gn value will be considered. Otherwise, it is further subdivided. So, this is a recurrence relation actually. A normal general procedure for control abstract, an algorithm can be written. If small p, then return solution for that particular p. Else, divide p into smaller problems, p1, p2, etc., pk. Apply the divide and conquer strategy. Again, same strategy. Return, combining the results. So, when we will get this return combining the results? If this result is satisfied, from there onwards, we will get the solutions for the previous levels one by one actually. So, this can be represented as a control abstract we will call, or a general procedure of divide and conquer. By using this, we can process or solve the problems of complex having the large sizes of the problems actually. Specifically, same methodology used for each smaller size of the input, then you can apply this one. I'll give an example sorting. For example, you want to sort some 1000 elements. It may take more time. So we will use some divide and conquer. I'll sort first a smaller list, then I can go further. This division is continued till each sublist is having a single element. Single element means independently those are sorting, no? So then we will combine the consecutive elements. While combining, we will arrange them into combining or merging. We will use in a order actually, sort order. So this divide and conquer, complexity of many divide and conquer algorithms is going to be written or generalized form will be like this. That is t of n is equal to t of 1 for n is equal to 1, or a t of n by b plus f of n, where a, b are known as constants. So this is the generalized method. N is the size of the input and a, b are going to be constants. Depending upon the problem, we are going to divide our list into 2 sublists or 3 sublists or 4 sublists, etc. actually. So that's why if t of 1 is equal to 1 means n is equal to b power k. B power k means we are going to have whatever be the value here b, that is the n is going to be represented as a power of k can be represented. In such cases only we can divide our problem into subproblems of b subproblems actually. Okay. Various algorithms, already known algorithms are available which will work based upon this strategy, divide and conquer strategy. For example, binary search, quick sort, merge sort, Strasson's matrix multiplication. These are the applications of our divide and conquer strategy. We will discuss these 4 techniques: quicksort, merge sort, and Strasson's matrix multiplication as part of our applications of our divide and conquer strategy actually. In this video, we'll discuss only binary search. So, binary search. What is a search? Searching an element, any given data structure is known as searching actually. We will use currently array of elements. In the array of elements, I am going to search for a value v. Let us assume that. How to search? First, I have to compare my value v with the first element of array, second element of array, third element of array, and so on and so forth. When the first occurrence of element happens, return the position of the element, that is the index of the array where it occurs. Otherwise, it will be continued till end of the array. So, even till continued end of the array, if doesn't satisfy, what does it mean? That search is going to be unsuccessful. That means the element doesn't exist in my given array. But it will take lot of time. For example, if the element exists somewhere here, end of the list, it will take more time. We will call such type of search as linear search. We would like to reduce the complexity of the search process. That is binary search. How to use this binary search? Binary, the term itself indicates binary means 2. So, the given list of elements are going to be divided into 2 sublists. And we will search in the first sublist. If it exists, it's okay. Otherwise, we'll go for the second sublist. Again, we will divide. If the list is again still very large, then we can divide. This process is continued. We will, whether that particular element is found at any iteration or at any level, we will stop. Otherwise, search can be considered successful. What is difference between the previous explained linear search and current search? Linear search, every element is going to be searched. But in this binary search, every time the middle of the element is going to be searched. That means the number of iterations are going to be reduced here. But there is a prerequisite is there for this one. That means our list of elements must be already in sorted order. I specified is increasing order, but it can be a sorted order. Depending upon the increasing or decreasing order, a small logic is going to be changed in the algorithm. So the given list of elements are going to be sorted order, already arranged increasing order. Then we can apply binary search. If those are not ordered, we cannot apply binary search. For example, I want to search for a student in a list of students in my college. In our college general records. Generally, the records of students are going to be stored according to the hall ticket number, sorted order. Then we can apply directly binary search. It will take less time comparing with our normal linear search. We'll discuss further how it works. Then how can we say that this takes less time also. So how this will work? The problem is determine whether a given element present in the list or not. If X is present, then determine the position of the X. Otherwise, the position is going to be 0. That means not found. How to solve this problem by using divide and conquer technique? The values are going to be small enough if n value is equal to 1. If my list consists of only one element, I will compare a single comparison law, so I can stop actually. So this divide and conquer is going to be continued as long as our list size is going to be smaller. Up to what extent? Smaller means it contains single element. There I can check whether that particular element exists or not. How to process actually? This is the logic. Let A is in a given array and solution of the problem is equal to I. I means the index value. If X available at A of I, ith position if it is available, we will return the ith value. Otherwise, we will return SP value as 0. When it happens, your problem size is equal to 1 only. That is, n is equal to 1. If P has more than one element, then it can be divided into further subproblems. So a small technique can be considered here. How to execute our binary search? Choose an index j and compare x with aj. Then if while comparing, what are the possibilities? It may be our x is going to be less than the aj, or our x may be greater than aj, or our x may be equal to aj. Aj means an element at the jth position. If it is less than aj means what happens? X occurs the elements below the elements of the search. For example, I am using 22, 25, 36, 44, 53. These are the elements. I am searching for an element 44. Let us assume that. I am comparing with some element, a single element. Let us assume that. I am comparing with 36. So 44, my 44 is greater than 36. That means my 44 exists. The list containing after this jth element. That means I am reducing my list to j plus 1 position to end of the. If my value is lesser 1, the search area is reduced to the first half of the element. That means this binary search, it will check with a value, a particular element, and if it is current searching value is less than, the list size is reduced to the left side of the aj, and if the value is greater than, right side of the aj is going to be considered. Equal means it returns the jth position. Like that, size of the list is going on reducing actually. So automatically it happens very fast. But what is jth position? Jth position will be considered always as the middle of the list. Middle of the current list we are considering. Middle element. So when the list is reduced, same process is applied. Again, half of the list is again I'll check the middle element. The current element is less than middle element. Again, half of this reduced list. Greater than means next second half of the reduced list, and so on and so forth. So this is the logic we are going to use. So this is the algorithm. We are passing 3 parameters. A is an array of elements. N is the size of the array. X is the element for which we are searching for. Given an array A to N elements, non-decreasing order. Remember that. This is the prerequisite. If it is not in a sorted order, our binary search doesn't work properly. So I am using 2 variables, low, high. Low indicates the lower bound of my list. High indicates the higher bound of X. We can start from 1 to N or 0 to N minus 1. Either of the cases can be considered by us now. Whenever we are considering, it depends upon the languages sometimes. So as long as the low is less than or equal to high, we will continue the process. Low less than or equal to high means list contains at least one element. If low is greater than high means list doesn't contain any element. Exhausted the list. Our array is got exhausted. Then we will find the middle value. Middle position is equal to low plus high by 2. We are taking integer value here. So I am checking with mid value. Jth position is here. Mid value I am considering. If x is less than a of mid, then so if x is less than a middle element, if it is x is less than a of mid value means my x possibility of occurrence of x is the elements before this middle value. If it is greater, the possibility of elements is second half of the list. Equal anyway returns. So 3 conditions here. So what it is to be? If x less than mid, then what happens? My list is reduced. First half. First half ante low remains as it is. High will be the mid minus 1. Low remains as it is. That means lower bound is same. First half of the list means lower bound to mid minus 1 value. So greater than means mid plus 1 to upper bound value. So when I am reducing my list, I have to update my high, and when I am reducing my list to the second half, I have to update my low value. So either of them, based upon that, then automatically list is reduced to the half of the elements. So if x is less than a of mid, then high is equal to mid minus 1. That means first half of the elements are considered. Else if x is greater than mid, then second half ante ending value, the ending value will be the remain same. So that's why first value will be the lower value has to be changed as a mid plus 1. Otherwise return mid. Otherwise means equal. So it will return. By using this algorithm, we can compute or find the elements. Even unsuccessful search, it will reduce drastically the time taken because all elements are not considered here. Only every time middle element we are considering, number of iterations are going to be drastically reduced. Let us just consider one example. 5, minus 6, etc. 14 elements are there, 1, 2, 4. So x values are going to be 151 minus 14, 9. 3 values we are going to give a demonstration, and 151 exists. So suppose I have to get the successful search. Minus 14 also doesn't exist, unsuccessful search. 9 exists, successful search. That means we are searching for an element in the beginning of the list, we are searching for an element which is at the end of the list, we are searching for an element which is not at all available at all. So how the tracing is going to be done? What is my low value? I am writing. First I am considering the entire list. Low value is equal to 1. High value is equal to 14. And my mid position is 1 plus 14 by 2. Mid position value is 7. So low value is 14, high value is, low value is 1, entire list mid position. 7th element I have to consider. 7th value means 1, 2, 3, 4, 5, 6, 7. With the 54 I am comparing. When we are comparing 54, 151 is greater than 54. So what is my list? My list is going to be next second half. Second half means high remains as it is, low will become mid plus 1. Mid plus 1 means 7 plus 1. 8. That means now my list is reduced to 8th element to the 14th element. That means all remaining elements are not considerable by us. Now you observe how many number of elements comparisons are reduced to. Again I'll do the same process, recursive, iterative I have done in the algorithm, but we can write recursive algorithm also. 8 plus 14 by 2. So 8 plus 14 by 2 means 11, you will get 11th element, 8th, 9th, 10th, 11th. With 125. Again 151 is greater than 125. Again we have to consider the next half of the list. Next half of the list means our lower bound is going to be updated with middle plus 1. So my low value is equal to 12, upper value is equal to 14. That is from 12th to 14 elements are reduced. See how number of iterations are reduced. Similarly 14, you are going to get 12 plus 14 by 2, 13th element, and my middle element is going to be compared with the 13th element. Still it is greater than, then next half 14th element, it is equal to 14th element found. See how many iterations I have carried out? 1, 2, 3, 4 only found. Normal linear search, if you take up it to reach 151, how many iterations are required? 15 iterations. At the 15th iteration, we will get the output actually. So like that we are going to consider this binary search is more efficient algorithm while comparing the linear search, but prerequisite is sorted order. Similarly, searching for minus 14, first we are considering middle element. Middle element is 1, 2, 3, 4, 5, 6, 7, 54. Minus 40 is the lesser value, so this will be considered, this list. That is lower remains the same, upper is mid minus 1, 6. Again middle element is third element, 1, 2, 3, 0. Again lesser than value. Again lower remains 1. Upper is going to be, you are going to have your mid minus 1, upper becomes as 2. Middle value of 1, 2 is again 1. I am comparing with minus 15. Minus 14 is still less than minus 15. Then lower value remains here 1 and upper value is also 1. You are going to 1 plus 1, you are going to get 2. So 2 to middle value is 2, but it is not, the list got exhausted because lower value is greater than upper value. Repetition of the loop is going to be considered as long as lower bound value is lesser than or equal to upper bound. When it reaches greater than, we will stop. That means that the value not found actually. You take another example 9. Same way it will work it out, but still number of iterations are less. Comparing with the middle value. Middle value means 654 again. Less than no. So it will reduce 1 to 6. First and mid minus 1, that is 6. Again middle value is 3, 0. But while comparing 0, it is greater than. So second half means here. Second half means our low remains changed. High remains same. 6 will be the high. Low will be the mid plus 1, 4. 4 to 6, middle element is 5. Fifth element is equal. So found. So by this, considering this binary search algorithm, we can search for an element with less number of iterations. The time taken to search, because every time half of the list we are excluding from the search process. Every time you are removing half of the list means, avoiding half of the list means, then the time taken to search for the remaining element is not considerable. Then it reduces the time. So as we yesterday discussed, this is going to be worst case, average cases. It is big O theta of log n, but best case is means first time itself it is equivalent to middle element, then it is considered as a best case. Even unsuccessful search, worst case means unsuccessful search also, theta of n can be considered for all cases. But how to get this logarithm of n? We will use two techniques. One is we can write recurrence relation if it is recursive algorithm, or we can consider how this is going to be search process or search size is reduced, on what basis it is getting reduced, half, in which format the data structure will be represented. Based upon that also we can identify the time complexities. So we'll discuss these time complexities, how to analyze these time complexities of divide and conquer techniques if it is recurrence relations in the next video, as recurrence relations can be solved by using various techniques. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.